Indeed, I'm Zoltán Lehóczky from Lombiq Technologies, and why I'm glad that I'm here is because while we are not really a space industry player yet, we just entered or just have ambitions to get into the space industry. If I'm not too far-reaching, but I think we can provide a unique perspective from a software development standpoint. We are a software development company working on modern high-level applications, and our Haslier tool can probably provide something useful for onboard data processing in such a way too. Because day-to-day, we are actually doing web development mostly with open source Microsoft technologies. There's an open source web content management system called Orchard, where we are worldwide market leaders, and we work with companies like Microsoft itself, Live Nation, or the Smithsonian Institution. But we have a couple of R&D projects, and one of them is Haslier. But before actually talking about it, let's talk a bit about what we see is relevant here on onboard processing in the new space sector. There are FPGAs. So, of course, FPGAs are proven when it comes to their power efficiency and performance advantages, and they are widely available. Particularly, I would focus here on the Zinc family of devices. So, I'm sure most people here are aware that a lot of new space companies, KP labs included, of course, have some kind of onboard computer or payload computer that are built around Zincs, which couple an ARM CPU with an FPGA. However, FPGA development today, and that's also true for ground-based processing, still requires specialist knowledge, I would say. So there are pre-baked accelerated libraries, there are high-level tools, but still, if you want FPGA acceleration, you need to actually understand and be able to use FPGAs. Also, when it comes to space specifically, there are many SDKs. Every satellite or OBC manufacturer pretty much has their own SDKs. What's more, these SDKs are usually secret, hidden. You have to purchase the device and or the SDK to be able to look at it at least. Now, compare this to how app development works otherwise. So on the desktop, in the web, for a smartphone. You have all kinds of SDKs, mostly open source, readily available. You get all kinds of resources, development tools for free. This is not really what's currently in the space sector. But probably we can provide some kind of solution with the .NET platform and with our Haslier tool. Now, .NET, if you are not that familiar with it, is a software development platform which is cross-platform, runs everywhere, including Zincs. It's open source, both the SDK and the runtime, because it has a runtime because it's a managed environment. There's a garbage collection and all kinds of things that make executing your application safe. So the most thing that you can do is crash your app, but that's also quite hard and it's easy to recover, but you can't crash the operating system. And since it's a modern platform, development is easy. You can just do app development as usual, and you get all the modern tooling. You get modern IDEs, debugging, automatic checks like static code analysis, automatic testing, and everything that's in app development currently. And with Haslier, you can also get automatic hardware acceleration with FPGAs. So you needn't drop the performance requirements, because what Haslier is a tool that takes a computer program and turns it into a piece of FPGA logic. So not just any computer program, of course, .NET, but .NET is a platform. It's not a programming language. Actually, a lot of programming languages are supported, So C# is the most popular one, but also C++, for example, or functional languages like F#, or even scripting languages like Python or PHP, JavaScript. Now, imagine writing your synthetic aperture radar data processing code in PHP. Of course, I wouldn't do that. So you might have got the gist of it, that we are talking about, in technical terms, FPGA high-level synthesis that is very, very much focused on software developers and for software developers. You don't need to understand FPGAs. You just write code pretty much as usual, but you still get FPGA acceleration. So all in all, what we intend to do, or what we already have actually, is that if your algorithm is highly parallelized and compute bound, you get a performance increase. You also get a higher power efficiency, so the benefits of FPGAs, but it's still software development as usual with .NET, with all the modern tools. I would add, though, that this is not meant for mission-critical systems, especially since it's a managed environment. It's not determined. The runtime, the execution time is not deterministic. Well, of the software part, the FPGA implementation is, of course. So a lot of talk. Now let's actually switch over to a hands-on demo. And what I'm showing you now is a bit of code. I hope nobody is afraid of that. What we see here is an example of an algorithm that would be suitable for FPGA acceleration with Hasslier. As you also see, it's called parallel algorithm. Now, spoiler alert, it's a massively parallelized, it's an embarrassingly parallel algorithm. It's kind of an exaggerated example. It doesn't do anything too useful. It's just a synthetic example. It has some logic here, which pretty much simulates that we are computing stuff. And it does this in tasks. By tasks, I mean .NET tasks. You can think of them a bit like threads. The point here is that we will open or start this many tasks, 280 tasks. And the 280 tasks will run as 280 threads on a CPU. Well, not at the same time, because the .NET framework will make sure that there's no starvation of resources, but still you get those 2, 4, or how many cores. Now on the FPGA though, you will get a hardware level parallelism of 280. So we generate 280 copies of the inside of your algorithm. And this is all standard .NET. So I opened Visual Studio, which is a standard development environment for .NET developers. This is standard C#. There are pieces of Hasslier API, but the language is the same. Everything happens from code. You can debug it as code. It's just .NET as usual, except that you can automatically turn this into a piece of hardware with Hasslier. And let's actually see how that works, because I also have a development board prepared here. This is a Trans-Electro development board. Here in the middle, we have a Zinc development board, daughter board that's built around the Zinc 730. And now I opened a remote shell to it because it runs Peta Linux, of course, and I will run our demo. What happens now is that first, that parallel algorithm that I showed you is executed as software. So we'll see how the whole thing performs as simple software. Now, this Zinc has a dual-core ARM CPU clocked around 650 megahertz. So that's what we get on the CPU side, and on the FPGA we have the 730's FPGA clocked at around 150 megahertz. So the whole thing happened. Let's check out the results. Now, as we see, the software execution was around 25 seconds. So we do a lot of stuff. That's all right. Now let's check out the hardware execution time. which is down here. And altogether, it was around 330 milliseconds. So the hardware execution is about 100 times faster than the software execution, which is not a big surprise because we pretty much got a 280 core processor just for our application. Now, of course, FPGAs have limits. So this is a simple algorithm. It will be able to have that many copies, but even for more complex ones, you can get parallelism in the order of dozens, which is still a lot more than what you get with the 2 cores on the ARM. By the way, if you are interested what's behind the scenes, Hesslier generates VHDL. So this is a piece of VHDL that Hesslier writes. You can check out Hesslier. It's up on GitHub. I will share the link to it. You can also check out the VHDL code it generates. You can inspect how it works, but it's commented code, and as you can see, it's also formatted. It's still generated code, so it's not that easy to inspect. But you should be able to get the gist of it if you are interested. All right. That's probably cool, but is there anything else? Well, yeah, we actually support the Vitis environment of Xilinx. What this means is that Hesslier supports every Xilinx FPGA with Vitis support, with the Vitis SDK support, which includes not just all the Zing boards, but also the Alveo cards, for example, the high-performance accelerator cards found in data centers. So that means that if you are using Hesslier, well, you can write code for onboard processing in the high-level, safe, convenient environment of .NET that will run on board of a satellite or a drone or of a robot. And you can run the same thing on a high-performance accelerator card in ground segment as well, in the cloud or on-premise, the same code. But of course, when running in the cloud, you will have a much bigger FPGA, probably 50 times bigger. And those FPGAs that we support are available in every major cloud. To give you a bit of an idea of the results, apart from that single sample I showed you, and these are again sample algorithms that we have, again, up on GitHub. The benchmarks are also up on GitHub and their details. With the Alveo cards, the in-ground segments, we get something between 4 times and 34 times speed increase. And when looking at the power efficiency increase, that's between 20 and 120, which a power efficiency increase is nice, of course, but where this matters most is that this corresponds to cost savings. On Zinx, we have actually nicer results. The speed increase is between 24 and 120 times. The power efficiency increase is also 20-something and 150 times, depending on the algorithms. We want to have more use cases and in-orbit demonstration as well. That's the next step that we are planning. If you have use cases, please let us know. I would be glad to talk about it. We are also in a partnership with the Wiener Research Center for Physics, which allows us to test some scientific computations. And FPGAs are nowadays in every major data center, so it's a versatile technology to invest into. So pretty much that was it from me. If you are interested, please check out the SDK on GitHub. The source I've shown you and all the other examples and the results and everything is up there. And be ready, because I think that we'll see a lot more about FPGAs, both in ground segments and both for onboard processing. So thank you very much.